All right, so the next chapter is a natural follow-on from the previous chapter because we were concerned with determining how, at the end of chapter 7, we were concerned with determining how the electrons are arranged in the atom according to the shells and subshells and so on, all right? So the first thing I'm going to talk about here is a comparison between how the shells and subshells are arranged in a hydrogen atom, or one electron atom, and compare that to a typical multi-electron atom. And there are two main differences I want to highlight between those two arrangements, all right? So just to highlight, just to show you or point out, this is the first shell, which has a 1s subshell. The second shell has a 2s and 2p subshell. And then in the third shell, we have the 3s, 3p, and 3d subshells, and so on, right? Now you'll notice that as far as the hydrogen atom is concerned, where you have more than one subshell, they all have same energies, right? So the 2s will have the same energy as the 2p subshells. And the same thing is true when you compare 3s, 3p, and 3d subshells, and also 4s, and the same will be true for the higher shells and their subshells, right? That's the first thing you'll observe when it comes to the hydrogen atom. Over here, when it comes to the multi-electron atom, what you'll find is that the energies of the subshells will be different. So for example, here, the energy of the 2s subshell will be lower compared to the energy of the 2p subshell. And you see the same trend occurring when it comes to the 3s, 3p, and 3d, and the same trend occurring when it comes to 4s and 4p. And it is further complicated by the fact that what you'll find is that the 3d subshell will actually be of a higher energy compared to the 4s subshell. We're going to talk about that later on, right? So that's the first difference that you'll notice between the hydrogen atom and a typical multi-electron atom, all right? The fact that the subshells, in the case of the hydrogen atom, they belong to the same shell, they'll have the same energy, but in the case of the multi-electron atom, that's not the case. Another difference between them is that, generally speaking, what you'll find is that the energy of the shells themselves, in the case of the multi-electron atom, are lower compared to the shells in the case of the hydrogen atom. So for example, the 1s subshell, which is in the first shell, is here. In this particular atom, the multi-electron atom, the shell will be down here, right? So this shell here is a lower energy compared to this similar shell and subshell in the case of the 1 electron atom. Same thing is true here. This shell here, which contains the 2s and 2p subshells, will be of a lower energy here. And the same is true for the other subshell, all right? And the other shells, I should say, okay? So those are the two differences between the typical hydrogen atom and the typical multi-electron atom. And we're going to see how that affects how the electrons are distributed among the subshells and the shells, right? So this brings us now to the concept of electron configuration, all right? Whenever you hear this term or see this term, basically what it means is how the electrons are distributed among the electrons of the various orbitals and subshells and shells in an atom, all right? And there are two ways of representing the electron configuration. One way is by what is called the SPDF notation, and this is something that you may be familiar with from your introductory or high school chemistry, right? Basically, this is an example of the representation in this notation, right? Where the 1 in this case represents the shell, you know, it could be n equal 1, n equal 2, and so on. The S here represents the subshell, and then this 2 here written as a superscript represents a number of electrons in that subshell. So the way you interpret this is that the first shell, which contains the S subshell, has 2 electrons in it, all right? That's basically how you would interpret it. So we use this representation to show how the electrons are distributed among the subshells. And in fact, okay, I was about to go into some examples of that, but let's look at the other way of representing electronic configuration. So another way of representing an electron configuration is what is called an orbital or box diagram, right? And basically in this representation, the boxes represents the separate orbitals within each subshell, and we use arrows to indicate electrons. And arrows will be important in terms of their orientation, because as we're going to learn later on, and we talked about it earlier, electrons can spin in two different directions. Remember, we talked about the fact that there are two spin quantum numbers for the electrons. One is plus half and the other one is minus half. So that will come into play when we talk about this sort of representation, right? So just to give an example, the electron configuration of nitrogen is shown here if you're using the orbital or box diagram, right? And you'll notice, and this will become important later on, you'll notice that the two electrons here occupying the same orbital will be spinning in the opposite direction, which is a direct requirement of what is called the Pauli exclusion principle. The same is true here. So basically, in any electron configuration, if you have two electrons occupying the same orbital, those two electrons must be spinning in opposite direction. And there's a physical reason for that. You have to delve into some physics in order to appreciate why that is so. I won't go into that right now. Okay, so that's the orbital diagram. If I were to use an SPDF notation to represent what we have here in terms of electronic configuration, it will look like this. 1s2, 2s2, and then 2p3. All right. So this would be the SPDF notation, and below, of course, would be the orbital diagram representation. And there's a clear advantage to using the orbital diagram representation because it shows you explicitly how the electrons are distributed among the separate orbitals, right? The SPDF notation is kind of limited in that it only gives you how the electrons are distributed among the subshells, right? But remember, there are some subshells which have more than one orbital. So therefore, this diagram here gives you a clearer picture as to how the electrons are distributed among the different orbitals. Okay, so what we're going to do now is look at some rules for writing down the electron configurations of atoms, right? And these rules are for the atoms in the ground state. And remember, we talked about the ground state earlier. The ground state is the lowest energy state, all right, or the most stable state, right? So all these rules we're going to discuss is in relation to the electron configuration for the atom in the ground state. So the first rule is that electrons ordinarily occupy orbitals of the lowest energy available, right? So basically what this means is that in the ground state, the electrons will try to basically be assigned to the orbitals of lowest energy, all right? So this brings us to the Pauli exclusion principle, which I mentioned before, which says that one atomic orbital can accommodate no more than two electrons. And these electrons must have opposing spins. And we saw that in the example that I just showed you, right? If you have two electrons, if you have two electrons occupying the same orbital, then those two electrons must be spinning in the opposite directions, all right? Another way of stating this particular rule is that no two electrons in the same atom may have all four quantum numbers alike, all right? Okay, the next rule is that of a group of orbitals of identical energy, the electrons enter empty orbitals whenever possible. And this is called Hund's rule. And there's a term, I don't remember if I've seen this in your textbook, but there's a term that is referred to orbitals of the same energy. They're said to be degenerate. So orbitals of the same energy are said to be degenerate. All right. So the set of p orbitals that we saw earlier, right? We would call that a degenerate set of orbitals because they all have the same energy. All right. So what this is saying, what this particular rule is saying, is that if you have a degenerate set of orbitals, then the electrons, when you're assigning them, you would first assign them to empty orbitals. All right. We're going to see some examples of that first, right? And then it says electrons in the half-filled orbitals must have parallel spins. In other words, they must be spinning in the same direction. All right. And we saw that in the previous example with the nitrogen electron configuration. In fact, let me just show you just remind you. So you'll notice that the electrons will be added here, here, and here separately when you get to this sublevel, right? And you notice that they're spinning in the same direction, right? Now, if you have an electron spinning, let's say you can have an electron spinning in this direction, let's say, right? But that would not be the most stable. You see what I'm saying? It is possible for an electron to spin in an opposite direction compared to the others, but that would not be the ground state. The ground state would be where all the electrons are spinning in opposite directions. So let me clear this and scroll down. Okay, so whoops. So electrons in half-wheel orbitals must have parallel spins for the ground state. All right. Now, here's where some memorization need to be exercised, because what you'll find, and I mentioned this before, when you get up to, what was it, the 3D sublevel and then the 4S sublevel, even though the 4S is in a higher shell compared to the 3D, it turns out that the 3D sublevel is actually of a higher energy compared to the 4S sublevel. So it becomes important that you know the order of the orbitals. And this is the diagram that is used to remember the order of the orbitals, right? And I recall when I was a student, the way I would remember this diagram is that I'll take a sheet of paper and then I'll write 1s, 2s all the way down to 7s here. And then I'll start at the second shell and write 2p, 3p all the way to 7p here. And then I'll start at the third shell to get 3d, 4d, 5d, 6d. And you can write 7d here. And then you do the same thing for the fourth shell, 4f, 5f, 6f, and 7f. And then you draw the arrows as indicated. And then to establish the orders of the orbitals in terms of your energy, you follow the arrows from tail to head, right? So the first lowest energy orbital would be the 1s, right? Then the 2s, then the 2p, 3s, and then the 3p, 4s, and so on and so forth. And that's how you establish your orders. And then once you establish your orders, then you assign the electrons according to the rules that I just mentioned, right? You start with the lowest orbital first. If you have a degenerate set of orbitals, you pair them up before you start. You assign them singly before you pair them up, and then you just go to the next higher orbital and so on, right? And I think I'm going to show you a couple of examples of that, right? In fact, what I just discussed is what is called the Aufbau principle, right? The Aufbau principle is basically the rule that shows you or guides you in terms of how to assign electrons starting from the lowest energy to higher energy orbital, right? So just to give you some introduction as to how this works, the simplest atom, of course, is hydrogen. It has one electron, so that one electron goes right into the lowest orbital, which would be the 1s orbital, right? So therefore, the electron configuration of the hydrogen atom is simply 1s1. So for the next element, which is helium, right, to get from hydrogen to helium, you'd have to add one electron to what we have here. Now remember, each orbital can have a maximum of 2 electrons, right? So therefore, the next electron will simply pair up with the electron that was there before, but it will be spinning in the opposite direction. So therefore, the electron configuration of hydrogen in this case would be 1s2. The next element would be lithium, right? Now to get from helium to lithium, you have to add 1 electron to the structure of helium. However, the 1s orbital is already full because it has 2 electrons, which means that the additional electron would have to go into the next higher orbital, which would be the 2s orbital. So therefore, that's why the electron configuration of lithium is 1s2, 2s1, right? And then the next element would be, let me just write it down here, would be beryllium. And in the case of beryllium, you'd have to add 1 electron to this structure here, which means that the electron configuration would be 1s2 and then 2s2. And that's how you continue to get to writing down the electron configurations of other higher elements. Now, at this juncture, I want to introduce to you the concept of the noble gas core abbreviation, because as you can imagine, if we get to heavier atoms like cobalt or palladium, right, the electron configuration, if you were to go through the same steps as I described here, would be a long string of characters, right? If you go to something like tungsten or osmium, the heavier elements, it would be very low. And in a lot of cases, you don't need to indicate all of the electrons. So basically, it is easier to write down what is called a noble gas core abbreviation. Now, this is the way that you get the noble gas core configuration, right? So let's say we want to write down the electron, the abbreviated version of the configuration of lithium. Well, the configuration of lithium is this right here. That's a full configuration of lithium. 1s2, 2s1, right? According to the rules, what you do in order to get the noble gas abbreviation, what you do is that you look for the group 8 element that precedes the element that you're trying to write the configuration of. So in the case of lithium, the element that precedes it would be helium, right? Then you look at the part of the electronic configuration which is identical to helium. So in the case of lithium, that would be this part right here, all right? And therefore what you do is replace that part with the symbol of helium written in square parentheses, and then you write down what is remaining, which would be the 2s1, and that would be the abbreviated electron configuration of lithium. And that's basically what you do for all the elements, right? You identify that part of the element or of the configuration which resembles the group 8 configuration that comes before it in the periodic table. You replace all of that with that symbol in square parentheses for that group 8 element, and then you write out what is left. Now, you might not see much of a difference between this one and this in terms of the amount of characters, but when you get to heavier elements, and I think I have an example here. Okay, here's a good example, titanium. If I were to write down the full electron configuration of titanium, let me squeeze it over here. So for titanium, which has 22 electrons, that would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 22. So that's 3d2. All right. So this here would represent the full electron configuration of titanium. According to the rules that I just mentioned, what you would do is consult the periodic table to look at which element, which group 8 element that comes before titanium, and that would be argon, right? And the atomic number of argon is 18, which has 18 electrons, which is basically the same electron configuration as this part right here for titanium. So therefore, to get the abbreviated version, you simply replace what I circled here with the symbol of argon in square parentheses, and then you write down what is left, which would be the 4s2, 3d2, and that would be the abbreviated electron configuration of argon, all right? So that's what you get from the full configuration to the abbreviated. Okay, any questions so far? Any questions? Any questions? Only one person out there in Zoom. Feel free to ask your questions, Mr. Retzlaff. Okay, let's continue. So here's an example. Write the electronic configuration of sulfur using both the SPDF notation and the orbital diagram. So the first thing I will do is go to the periodic table and look up the atomic number of sulfur, which is 16, right? So for sulfur, I'll write down when it's asking for the SPDF notation. Again, you have to use that diagram, right, that I showed you, right? I remember I remember the configuration up to the third period. No, yeah, the third period. Beyond that, I'll have to consult the diagram myself. So, so in the case of sulfides, 1s2, 2s2, 2p6, and then 3s2, and then 3p4. Oops, 4. So that would be the full electron configuration. And just by the way, even though the question is not asking for the full electron configuration, what do you think the abbreviated electron configuration would be? What would be the abbreviated? Even though the question is not asking for that, but
it's Ne 3s2 3p4.
Ne in square parentheses and then 3s2 3p4. Very good. All right. Now to get the orbital diagram, right? The first box here would represent the 1s orbital. The second box here would represent the 2s orbital. And then you're going to have 3 boxes here for the 3p orbitals in the second shell. So that would be the two p orbitals, right? So the first two would go here. The second two would occupy the 2s orbital, and then now for the 3p sublevel, this is how the electrons will be assigned. 1, 2, 3, right? Because remember, you have to spread them out among the degenerate orbitals first. And then the one extra orbital, which will be the fourth electron in that sublevel, can go into any one of these 2p orbitals. I'm just going to put it here. And of course, it must be spinning in opposite directions if they're occupying the same p orbital. And that's it. All right. So that's basically the answer for this exam. Right? Any questions?
So we don't need 3s orbital and 3p orbital?
Oh, right. Sorry. Thank you. That would go here. My bad. So you should have two here. Hold on. Oh, wait a minute.
There should be 2.
Yeah, my bad. Thank you. I don't know what I was. There should be another 3s orbital. My bad. So there should be a box here. Which is 3s. And then so these are actually completely occupied. I'm sorry. And then you have these 3p orbitals, and this is where you have this situation. All right. So you have 3p here. Okay. All right. Any questions about this? Any questions? Okay. So based on what we have covered so far. Oh, wrong. Too early, man. I'm going to get you started on assignment number 8. What time is it, buddy? Oh, that's why they came so early. Okay. My bad. All right. Let me get you started on this. We'll do the first one. We won't have time to do the rest. So let me bring this up on the screen. Let me go here. No, not there. There. Files. Assignment number 6, number 8. Okay, so for those of you out there in Zoom, I'm going to publish it now so you will have access to it. Okay, so what I'm going to do is let's do the first one in part A and the first one in part, I'm sorry. The first one in this section here and the first one in this section, all right? And then we call it today. So for sodium, the first thing you do is what? You look up the atomic number, which is what? 11, right? So therefore, in the case of sodium, it's going to be 1s2, 2s2, 2p6, and then 3s1, right? Because what this question is asking for, I should have pointed this out, is asking for the unabbreviated electron configuration. So that's a full electron configuration. Now for cobalt, right? The electron configuration for cobalt is
It's 27.
okay, the atomic number is 27. Okay, so 1s2, 2s2. What I'm doing first is writing down the full electron configuration. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3b5, right? That's 27, right? So that's, okay, good. So this will be the full electron configuration, right? So the next thing we have to do is ask ourselves, what is the group 8 element that comes before cobalt? And that would be argon. So therefore, argon would represent this part right here, right? So therefore, the abbreviated version will be AR in parentheses, and then 4s2, and then 3b5, and that's it. All right? So based on that, I would expect you to be able to do part A. Let me just check something here. Okay, in fact, you should be able to do all of part A. So I would focus, if I were you, on part A for now. Do it, attempt it. If you have any questions, we can come back to it, all right? You can listen. You can come back to it and I can answer the questions that you guys can have, all right? Okay, so that's it for today, folks. Okay, here it is. And oh, Mr. Ratcliffe, that is gone. All right, so let me get over here.